So we just did the recap and checkpoint, but technically we're on module 4A, data preprocessing. Okay. So I don't know why they broke it into two parts, maybe because we're going to take lunch in the middle of it, but we're going to talk about data preprocessing, and then we're going to talk about data preprocessing, and then we're going to do a lab, and then we'll probably do a little exam stuff. We might talk about model training, but I doubt it. Okay. So if you're not taking notes, please take notes. If you're already familiar with it, then check out. I won't be offended. Okay, so we're now moving past problem formulation and business definition, problem definition, to basically collection integration, which is what we're going to talk about now, as well as data preprocessing and visualization. Now, this is where you're going to source your data and collect it. You might reformat it and or reframe it, and you might clean up quote unquote dirty data. Why do we say dirty data? What data just needs some processing. All right, so first, I know it's going to be a shocker. You're going to be like, what, Michael, you're going to be crazy. Yeah, no, you're going to get it from different sources, right? You're going to have transactional databases, transactions themselves, click streams, analytics, tons of data from IoT. I mentioned the Sentience platform that I worked on. It was like data from plants, like temperature sensors, motion sensors, barometric pressure, all kinds of stuff, right? And then servers, disks, multimedia, social media. Although I think servers and disks kind of like same thing, but whatever. Maybe servers and storage, servers that have storage, and then storage services, multimedia, social media. So just talking about the different like various kinds of data you can get access to. Now, and then how do you generate labels for data, right? Yes, CSV files emailed to you. Yes, that's fun. And by the way, some of this is structured, semi-structured, unstructured, right? It could come, by the way, from Redshift, which is a data analytics warehouse. It could come from the data lake, like Lake Formation, which is just an S3 backed data lake. It could come from DynamoDB, which is a NoSQL database. It could come from RDS, which is a transactional database. I mean, S3, Elasticsearch. I mean, Amazon has like 11, 12 different database technologies. It could come from Kinesis, which is Amazon's proprietary Kafka, which they also have Kafka. So if you want managed Kafka, you can do that as well. So it's like there's just so many services out there. Now, with the data lake, it usually happens is that this data is usually centralized. So it's readily available to be categorized, processed, enriched, and consumed. And usually there's a data catalog, right? So there's a data catalog that will allow you to identify the data and whether it's been cleaned in some way or processed, or whether it's just the raw data, right? There's no silver bullet for this, by the way. When done right, this can work really well. When done wrong, it's kind of just as bad as having 30 different disparate data sources, right? So, wait, Dylan, someone sent you a screenshot of an Excel spreadsheet? That's horrific.
Yeah, like an image, so you couldn't even copy from it.
Yeah, that was my first thought. That means you had to manually recreate it, assuming they put that on you, right?
Yes.
Sorry, man, that sucks. Well, now we need some image recognition to extract numbers from a picture of a spreadsheet. Which is someone's written something like that. Let me know when you make a lot of money off that. So, so S3 does provide standard backing, like for data lakes. As mentioned before, when we were talking about life cycles as a word applied to S3 versus applying it to SageNIC or notebooks, it does have like multiple tiers of storage. So you've got standard S3, which is the hottest. You've got intelligent tiering, which is kind of a more mobile, it like moves it to different classes. And then you've got standard and frequent access, and then one zone of frequent access, which is what IA stands for. And then you have Glacier, and you have Glacier Deep Archive. So just know that you go from hot to cold there. There's different kind of challenges around that. But the idea basically is that since S3 will scale infinitely according to Amazon, it's a great place to just submit data, do ingestion processing, aggregation. You can even do some analysis off of it, and obviously some search capabilities as well. So remember, S3 tends to be the source, right? you do in general need to know that Glacier is the archival process, and that infrequent access is cheaper than standard S3. But I don't know that you need to be able to rattle them off, right? I think you just need to know that there are colder tiers of storage, and frequent access is one of them, and that Glacier is the coldest, right? Glacier actually doesn't offer direct access. Glacier is like putting it into a backup vault. You have to restore it before you can actually access it. The other tiers you can access live, right? Without having to do anything. But they don't go very deep on that, Karita. Yeah, but they do mention it. Yeah, that's exactly right. So analytics bucket goes to a training job, which then the model artifacts are generated out, and then you've got like a SageMaker deployment at that point in time, which, I know this sounds weird, but you train the model, and then once the model's trained, you can then deploy it with that either online, like on demand, if you will, or batch processing that we referred to earlier. So, S3 plays a role in hosting pretty much both the inputs and the outputs. It is worth mentioning that, I think if I remember correctly, S3 can like on a single file get about like 3,500 like reads a second. It does depend on what else is on that partition. There are ways to speed that up, by the way, by either structuring your data into protobuf, which don't worry, we're still going to talk about that. I haven't forgotten that from day one, from yesterday. But there's ways of structuring your data so you actually get like a lot more performance out of it. Now, we're going to talk about the different modes and stuff like that as we go forward, but just be aware that if you use S3, there's ways that you want to structure your data so you get better performance out of it. And that does figure on the exam. How often are batches run in a batch deployment? How often are you submitting batches? Really, Chris, that's the question. If you submit an entire data set, then that entire batch is going to run, right? You can schedule it, by the way, but it depends on how many times you execute it. It's still on demand in the sense of that you're submitting an entire batch, but with an online deployment, you're submitting one like request. I want an inference. With a batch set, you're saying, I've got all of these requests. Give me inferences for these. Okay. All right. So in addition to using S3, as we kind of step up the tiers of storage that you could possibly use, you can also use EFS. Now, S3 is not meant to be mounted inside of a file system. You have to pull the files back from S3 onto your local disk and then process them. It does have a pipe mode that allows you in a sense, to stream the data, straight to the instance and allows it to start processing once it hits a checkpoint. So EFS is a little different because this is a network file share, which means it could be mounted on your like notebook instance and then kicked out into production to deploy like another model, or mounted into another instance, or mounted on your home directory on your like workstation that you're using to mess around with on AWS. So EFS, by the way, can be shared with multiple instances. So, and it can be written in, it can be read and written to like it's a shared file system, like it's a disk attached to the box. NFS, by the way, has been around for a long time, at least since the late 90s, maybe mids actually, maybe longer. And so EFS is just Amazon's implementation of a network available file system, almost like a drive letter on Windows. But I just want to caveat this is that EFS is built for Linux. So it's not built for Windows. Amazon has another service called FSX, File System X, for Windows Server that is built for Windows boxes. But most of all this is done on Linux. If your training data, by the way, is already on EFS, it just gets mounted directly into the SageMaker instance. And so there's no data transfer. It launches directly from the file system on EFS. And by the way, you can turn the dial on performance on these EFS file systems pretty high. So you can get really good performance off of them. Now, let's say that S3 isn't fast enough, EFS isn't fast enough, and you're like, I need to go faster because you've got Ricky Bobby syndrome and you know, if you're not first, you're last, right? So what's going to happen is that then you're going to look at something like FSX for Lustre. Now, notice I didn't say FSX for Windows, because FSX as a service inside of Amazon has 4 different flavors of network file system it can share. Why? Seriously. Anyway, it's got Lustre, which Lustre is an open source project that is usually used for high performance computing. Lustre is a file system service, and it basically, what it does is it copies the S3 data into the Lustre file system on your box, and then the data gets processed by SageMaker. Now, be aware that then that subsequent like runs or iterations against that data, including the model generation, are super fast because it's not going to be pulling it off of S3. So think of Lustre almost like a cache, right? So it's going to load your data ahead of time. Also, like this is a little bit of a misnomer. You can actually write back to S3 through Lustre. In a weird kind of turn of events, Lustre will actually mount S3 buckets into the file system, which, by the way, is typically a huge no-no, but it makes it easy for you to read and write data directly to your S3 bucket from a file system that's attached to your like notebook. But here's the main thing you need to remember about this is that this is the main thing you need to remember. S3 is great, scales better than any other service, not really mountable into an operating system, and therefore is slow because it's an external storage system. Slower. EFS mounts directly into the operating system. It's faster. FSX for Lustre not only mounts directly into an operating system, but it can talk to S3 as well and will cache from S3. And FSX for Lustre is the fastest. Now, I also want to point out, by the way, that we just went from cheapest to most expensive. So cost-wise, Lustre is not as cheap as S3. So Keith, whenever you launch a notebook instance like a virtual machine, it always has EBS attached to it when it comes to SageMaker's perspective. And so you just need to make sure that your EBS volumes are large enough to handle your data set. But I just want to tell you this is that you're limited to 16 terabytes on EBS. So, sorry. So you're limited to 16 terabytes on EBS. So if your data set's larger than that, you're going to have to host it on another file system. But mainly the EBS volumes, the disk volumes that are attached to a notebook instance, they are ephemeral. So they're just not going to permanently stay there. Does that make sense? So think of EBS as a virtual hard drive that's just going to be, it's like a temporary drive there. Yeah, so it'll be S3 to EBS. That's assuming, by the way, that you're using what's called file mode with S3 versus pipe mode with S3. And some of you are like, Michael, what are you saying? So S3, by the way, has 2 modes. You can do file mode where you copy the file over to the local disk attached to your notebook instance. Let me say that again. S3 has a file mode where you copy the training data out of S3 to your local disk attached to the notebook instance. And then it has a pipe mode where you stream the data directly to the application that's doing the processing, and you don't have to wait for any files to get copied. It just runs. So in both cases, there's a little bit of scratch volume, like temp stuff that happens against the EBS volume. Okay. So EBS is not really, you're not going to host your training data on EBS. It's just going to get copied there temporarily. Notice I'm saying EBS instead of EFS, so make sure you don't confuse those two. These are all network file shares to a certain degree. S3 is really not, but like they're available across the network. EBS is directly attached to the notebook instance. Okay, so these are your data options. Questions that they're going to ask you on the exam. I need super fast load times for my training data. Lustre. I need the cheapest storage that can handle massive amounts of scaled data. S3. I need to archive data after 6 months. Like I need to archive my training data after 6 months into the cheapest storage possible. S3 Glacier. or Glacier Deep Archive, whatever. If it says with the word Glacier in it, look for Deep Archive is cheaper, but just letting you know. And then EFS is going to be the option that you choose when you're looking for that middle of the road, or Lustre is not an option for network file shares. Sometimes they'll give you answers where EFS is the only answer and they won't list Lustre, and so EFS is the next best answer. Okay. Okay. Questions? Lustre can connect to multiple instances. So Lustre is just like EFS. It's a network file share. It can connect to multiple boxes. Okay. Okay. All right. So let's see. Let's think back to our fraudulent transaction scenario. Okay. So customer, was this fraud? No. Okay, cool. Let's see. So before you can start running statistics on your data, you might need to understand a little bit about what you're working with, and you have to make sure it's probably in the right format to be analyzed. So how do you get your data into the proper format? So like basically, what are the problems with the data? What would you use to fix it? What tools are available, right? So pandas, again, I work with weird people who call them pandas. Is an open source Python library, right? It can be used for this kind of like data formatting. For example, let's say that you needed to reframe or reformat the data with like only certain columns in this whole space. You can use Panda to do that. Now it'll do a ridiculous number of data formats like CSV, TSV, JSON, Excel. There was one I saw in there called Pickle. There's a bunch. So what can you do with data frames? Well, you could take, for example, two disparate sources, like two columns from two disparate sources. You can put them together, right? You put that in data frame, and data frame is made up of many series, which are basically columns that are like holding these particular data types. So, and the axis labels are referred to as the index. So for this, you can calculate statistics, you can clean your data, you can visualize it, you can store the cleaned and the transformed data. You can also convert it back into its original format. So, there's a lot of options here. Here, they're importing the module / library pandas SPD. And then what they're doing is they're just reading a CS file. Sorry, a CSV file. So Orc, Parquet, I mean, Arlo, there's like a bunch that it will do. I think there was, let's say I had a link for that. Panda. Oh yeah, there was. So there you go. Ridiculous number of options for data that you can source and export into. Hey, what's going on, buddy? Hi. Is there a reason all of a sudden you're slowing down? Oof. God, I did not like that. Did not like how quickly I kicked the keyboard shortcuts there. So there's Pickle, by the way, binary format, Orc, Parquet, Feather, Open Document. So I mean, if you're looking for it, it's listed there. Which doesn't mean it does them all. It just means that's the list of what it does do. So this is Panda. Panda, by the way, is going to figure into your lab today. And remember, don't freak out. You're going to have a blank sheet and you're going to have a solution sheet. So you can bang your head against the wall in order to figure out what to put into your like your blank one. And you can always fall back to the solutions, right? If you need to. So now here, you can make sure your data frame is constructed by at least like outputting like the first, like in this case, 3 rows, right? So this can be useful for when you think you're going to convert into a data format and you like want to see, for example, the first few rows of the data frame. So we read the CSV and now we're going to basically present out, hey, this is what we see right here. You can also see the shape of the data. So for example, 3 rows, 5 different columns, right? So let's see, and then here, oh, I want to see the column names. Yeah, so dataset.columns, house number, occupants, primary occupation, is married, that kind of thing. I don't know that that relates with what we were just looking at, but still, that must be a different CSV. Okay, so these are pandas. So basically framing, manipulating, kind of like formatting data, right? Shaping it, editing it, right? There are a bunch of other libraries that are used for different purposes. These do figure on the exam in the sense of they're not going to ask you to declare it in Python, but they're going to ask you to understand what they're used for. So let's talk about them. So NumPy, which is pretty well known, I think it was one of the first actually that I remember touching. It's basically it's just for you doing scientific computing, right? It's general purpose, array processing package, right? And it's just a package for working with these arrays, right? I think actually the first time I touched it is because I was actually touching Fortran code. But like you can do linear algebra, you can do random number capabilities, you can create, whatever dimensions of array objects that you want. It is a common tool for pre-processing, and it can help you reformat your data and run statistics on it to better understand it. So that's NumPy. So just know that this mainly is a kind of array manager, does linear algebra, and has random number capabilities. Okay. Scikit-learn, which Sickle, Skittle, I work with people who label these things for some reason. It's an open source library that basically has, it does basically data mining and data analysis. Now this is built on some of the other packages, including SciPy, which we really don't talk about all that lot. And it can be used in every phase of the pipeline, including data preprocessing. And we're going to circle back a lot to Scikit when we go through the model training phase of the pipeline as well, because the library includes supervised algorithms, right? So it does have linear regression, random forest, clustering and k-means. So it will actually also run supervised algorithms as well. That's Scikit. So we did NumPy, Scikit, Scikit-learn, sorry, Scikit-learn. And then the last two are really about visualizations, right? So matplotlib is used for two-dimensional plots in mainly of NumPy arrays. So you usually find them working together. You can get lines, bar charts, scatter plots, histograms, that kind of thing in here. And you can leverage it directly in your notebooks, which you're going to see actually in the data processing section. Seaborn is built on top of matplotlib and does work with data frames. So typically you'll see in code that, all four of them will be imported together, right? You'll see scikit-learn along with NumPy, along with Seaborn and matplotlib. So, and the thing I think that's better around Seaborn is that it does a lot more attractive and informative, statistical drawing. So it'll do more things like coloration and distinctions, sizing, triangles for certain anomaly data points and stuff like that. Seaborn tends to, matplotlib is been around for a long time. Seaborn is kind of an enhancement layer on top of it. It makes matplotlib prettier from my perspective. Okay, so those are just the general libraries. So NumPy for array and some algebraic random number, basically array management. Scikit-learn, which does data analysis and pre-formatting, right? And then Panda frames, which can be used to manipulate data, prune data, that kind of thing. And then you've got matplotlib and Seaborn, which are both visualization libraries. Seaborn's a little prettier than matplotlib, and Seaborn's built on top of matplotlib or matplotlib. Okay. So brief run, which by the way, you're going to get your hands on with this in the lab. Run the libraries. The other thing is how do we clean up dirty data? Now, for example, if you look at this, is there anything that kind of stands out when you look at this data set, that your eye is immediately just kind of drawn to? Okay, good. So missing data, That was one. Income units is another. Education needs to be cleaned, maybe. Yeah, like what is this? Right? The guy with H. Well, I mean, we should probably talk to that guy. He's probably in Bitcoin. Who knows? Although he's making a consistent salary, so maybe not. Sorry. Wrong data in the state field. Yep, that's another problem. Could be an outlier, Angelique. Absolutely. Doesn't necessarily make it wrong, right? Education's under state too. Yep. Education under state. Inconsistent measurements. And somehow somebody's 154 years old, right? Yeah. And then of course, look at all these data gaps, right? Data gap here, data gap here, data gap here. Cool, Chris. I'm glad that you're 154 years old. You look great for 154. Wow, Jonathan, smart people don't live in outbreak zones. That's what we're deriving already from our analysis of the data. Yeah. So anyway, there's a number of challenges here, right? So let's go take a look at some of these. Maybe we won't revisit maybe our prejudices around people being well educated and living in outbreak zones. So one, obviously, we didn't expect to see baccalaureate. So things like converting everything to lowercase, kind of like normalizing spelling errors or doing fuzzy correction. Those are all appropriate. Make sure it's all in English, that kind of thing. You might even like convert deviations, like baccalaureate degree, right? Might convert that into something standard. Make sure that everything's kind of set to the same kind of like categories. Sorry, I didn't go for the oulat there. Sorry, my apologies. And then obviously scales need to be corrected and set, right? And so, you need to do some discovery on your data to find out if things are relatively homogeneous, if they're scaled the same. Are there outliers in their data? Are there gaps in your data? Again, outliers aren't necessarily a problem, but just know when there's a wide range of statistical differences, especially between correlated numbers, that can get like really weird, especially when, for example, like there's a key dimension to your data that scales from like 1 to 15, and there's another dimension to your data that goes from 1 to 3 million. Depending on the granularity of the data, that could get really, really weird, right? I'm not even gonna say that word again because apparently I'm offending people. Just kidding, Jonathan. And then, obviously, like more than one feature in the same column, because obviously that should have been in education, not in whatever, right? In state here in this case. So you have to reshape the data a little bit. And then, so you're gonna get the data scientist, for example, to normalize the column. So these are the things that you're gonna think about, and we're gonna talk about this a little bit more in the next section on processing. And you're gonna spend some time kind of in your labs trying to understand these kind of dimensions and what to do with these gaps and whatnot. Now, one question I have for you is, what do you typically, for those of you who have been working in the space for a second, what do you typically do when you have an empty field inside your data? Do you drop the row? What are some options that you've thrown out in the past for blank data? Because the other stuff is pretty obvious, right? So impute, by the way, just so for those who are aware, impute values typically means let's put some kind of alternate meaningful value into that. Let's impute a value in there, right? For example, the mean of all like the incomes, for example. But we do have a huge outlier in the outcomes, so we might have to be careful with that, right? If there's a correlation, we can do supervised learning, right? If there's some label that needs to be applied, we could potentially also try to derive like topic grouping, in some form or fashion using unsupervised. If it's a small number of records, remember, gapped records in a small set are going to have a huge impact. So it might be worth dropping it, especially if there's a huge outlier, right? Like for example, if you had a row with like 3 or 4 outliers, you might drop that data, but you would declare it, by the way. So remember that whatever you do to this data, make sure you capture what you've done to the data explicitly. And the great thing about doing it in code is that typically there'll be a record of it, right? Yeah, heavily depends on the proportion of missing data to the total records. Absolutely. So there's a couple of different ways to approach this. We are going to talk about it. I just thought I would speculate for a second to see what people have done. So imputing values means deriving some kind of meaningful replacement. So if you see the word impute, right, instead of input, what we're saying there is what we are calculating some kind of decent replacement, some kind of meaningful replacement for the data, whether that's an average of the numbers or an impute of the most common, most frequently used category, right? Let's say A is there 10% of the data, B is there in 80% of the data, and C is in there for another 10% of the data. We could probably reasonably get away with B because it represents 80% of the data categorization for the three categories that exist in that particular like row column in that particular field, right? So not asking you to have any answers for that right now. We're going to talk about the ways in which you can impute data into the system, okay? Just want to get your thoughts flowing here. All right, so let's talk about the next data processing. I don't know why they split this into two, because honestly, we could have just kept going. Let's talk about the next data processing set. Okay, so we're going to continue with data preprocessing. So from a recording standpoint, by the way, this is just going to be the same set. Typically, that's a pretty safe bet, Jonathan. It does depend on the number of records, right? But if like 80% of like 10,000 records is going to be New York, it might not be a bad impute, if you will, to put New York in there. And so that is actually on the exam questions. So, and that is the answer for that, if I remember correctly. My only ask is that be methodical. Whatever it is you do to the data, make sure you know exactly what you've done to the data. So then that way, when you go back and you're evaluating the impact against modeling, you know what you've done and what you haven't done. I only say that, by the way, because I work more in the data processing, ML ops kind of like side of things, working with teams to execute this. Sometimes they come back and they'll say like the model is bad, and it's like, well, what did you do? Like you've ran 20 of them. Why are 18, 19, and 20 off? And they're like, well, I did something to the data, but I don't know what it was. And so then you kind of try and reverse engineer what the changes were. No, that's unnecessary work. Okay. So let's continue to talk about data preprocessing, talk about how you can visualize the different features and stats. And then we will talk about imputation. Anyway, it comes up, I think, and it's either in the next module or the next module. So we are going to talk about it, how to replace data. Okay, so we've got outliers in the data, right? And so first of all, how do we identify these outliers, right? How do we determine if they're appropriate or if they need to be changed or removed, right? So with pandas, for example, you can call on the shape of the object to see the dimensions, right? So that's useful because it can tell you kind of like how many rows and columns. You can get summaries of whether you have numerical or categorical data, right? You can just basically call the shapes. Now, for categorical attributes, you can actually look at the frequency of the attribute values in your data set. In other words, how many times does, what's the most frequent category that shows up in terms of state? What's the least frequent? Obviously, Wyoming, right? Flu shots, most frequent, yes, no. How many unique values? So then you can reconcile the number of unique values with least and most frequent, right? Get some idea of what's happening. Now, most frequent in here, I love this, is $45,000 a year. Least frequent is 3 million, I would think so. And then the mean and the median, right? So basically mean being average and then median being kind of like, what are the middle numbers out of the range of values, right? Other things that are significant here, like, first of all, why are there 52 values for states? You want to tell me why? I know some of you have done this before. Yeah, territories, right? DC and Puerto Rico, right? So like knowing, like, for example, you can look at the class distribution, for example, to see if there's an imbalance in your data set. Imbalanced data, by the way, can mark a really like disproportionate ratio of classes. For example, if your data set's made up of credit card transactions, but only 1/10 of the percent of the data is labeled as fraud, well, I gotta tell you, it's really gonna be hard for your algorithm to learn how to identify fraud if only 10% of the transactions are fraud. Now, you can do that by doing some kind of data pruning if necessary, depending on the amount of data you have, right? So there are ways to manipulate that. To go kind of like look at mean and median just a little bit, by the way. So mean and median are two different measures describing to the extent at which your data is kind of like clustered around some value or position, right? So mean can be, the average can be useful to understand when your data is symmetrical or when it's not symmetrical. Typically there's the same when the data is symmetrical. Typically they're skewed if the data obviously is asymmetrical, just in terms of the general data distribution. Chris, and a lot of the things like, I'm trying to think of the book that I was just actually looking at, and they typically recommend somewhere between 50, 60, and 70%. Like usually a good half of your data, or just slightly less, is actually trained, right? That way it can make a clean discernment and it's not just random. But I mean, I feel like I've trained models that had like 80%, like 20% fraud data, and they actually did really good. So in some cases you work with what you've got, but ideally you would get closer to 50-50 from most of the recommendation models that I've seen. But I will tell you this, is that since most of the time you're just trying to get take load off of a human being, if your model can just identify with certainty a certain percentage of that, then it's still actually really good. So even if you're not getting the 80 or 90% identification thresholds, as long as with certainty you can identify the 60 or 70%, it can still be useful. So, but 50% is tended to be the ideal number. Here, by the way, mean and median match, right? Because it's a symmetrical kind of distribution of data. Here, there's a couple of high incomes that are kind of dragging the mean up, the average up a little bit, right? Yeah, and smoke, by the way, is definitely on the exam, so we'll talk about that for half a second, James. Yeah. Smote is interesting because it allows you to oversample adjacent data and create meaningful kind of like copies of adjacent neighbors. So anyway, something we're going to cover that when we get to the practice exams, just to make sure I'm clear about that. Outliers, by the way, like for example, in the human brain is pretty good at this. Immediately, you know where the outliers are, right? So moving past kind of studying the shapes and dimensions of your data, outliers are points that exist in your data set that are kind of abnormal from kind of the general clusters of values. They're not always something you want to clean up because they can add richness to your data set, but they can also make it harder to make accurate predictions because they can really skew values away from other kind of quote unquote normal standard values related to the feature. So it may also indicate, by the way, that the data point actually might belong to another column. Meaning, for example, maybe instead of asking income, maybe it's there's another like dimension or label you can add to the data that says, look, if you're making under $10,000, you're in this column. If you make within this range, you're in this column. If you make 200,000 and above, you're in this column. And it just depends. Adding those kind of artificially engineered categories to your data set could make it more meaningful. You have to be careful though, because when you add dimensions to your data, you can cause things to overfit. You want to be, and again, it's something we'll talk about in model evaluation. So, but like, let's see the impact of an outlier, right? So look at these two data sets. So the mean is at 15.57. You got a median of 16, a mode of 12, which by the way mode is really just what's the most frequently occurring value inside the set. And then kind of your standard deviation, meaning deviation from kind of, well, Actually, you know what? We're going to hold off on that for a second because I'm going to come back to that. But just looking at like just its impact against, for example, mean as an example, when we added 300 in there, notice that the mean, the average went way up, right? And that value is literally 280 points away from the next nearest value. And there are no in-betweens in there. But does that mean you drop it? Possibly, right? And consider this, right? $300 million a year. Is that a natural or an artificial? What does that mean? Is that, in other words, was the outlier like just accidental, or is it a natural outlier, meaning it is actually existent in reality, meaning that it is actually the true, it is true data being represented. It's not just a mistake, right? An artificial outlier, by the way, you know, like someone made a joke earlier in chat. They were like, hey, the person probably fat fingered 154. And that would be that would be totally valid, right? Because I mean, I don't know if the value should be 54 or 154. I'm sorry, if it should be 54 or 45 or 15 or 14. I don't know what the value is. But you know, honestly, at that point in time, mean imputation, where we might take an average of the other ages and throw that in there, or we might do a little bit of like oh God, my brain, it's not working. There's a methodology where you can like correlate it with other values. For example, how does age relate to income, for example, and other aspects, and then you could come up with a meaningful number based on that like algorithm. Sorry, I can't remember what that's called for some reason, but basically where you derive context by looking at the other values and how they relate to that number. Yes, thank you. Or mice, that's what I was thinking of, right? Mice in particular, where you could basically derive a value based on what the other contextual values and their relationships are, their correlations with the other dimensions of data. Let me be specific about that. So like if at age 39, we're making $45,000 a year, and notice this person is making $53,000. If we can find other correlating values that between the age of 45 and 55, sorry, between the income of $45,000 a year and $55,000 a year, you know, the average person's age is going to be 43, then maybe we put 43 in there, right? There's meaningful ways to do that, to replace artificial errors, especially numerically, with contextualized, like supervised learning errors. Now with the natural outlier, so with the artificial, you know, honestly, you could delete the outlier, or honestly, I'd probably do some computation to impute something meaningful. With a natural outlier, here's the challenge, is that you could transform the outlier. Here's the problem though. If you know it's natural and it's real, I'd be more inclined to kind of drop the person from the data set, but you know, that could cost you a lot, right? And especially if it's real, it means that in reality, right, you're actually getting real information about that someone is making this money and they have these characteristics. So that's meaningful data. So it's probably more likely that you might look at mean imputation for that value, or you might transform it, right, to just reduce the extreme variation. So you could take the natural log of the value, which in turn would reduce the variation caused by the extreme outlier, and therefore the outlier's value on the data set. Now you might want to experiment with that, right? I'm kind of surprised they actually like are recommending like using the mean of the feature. I don't really, as a general rule of thumb, and I would love to hear if anybody has a dissenting opinion, I don't tend to use the mean unless it was caused by artificial outlier. If it's natural, I don't tend to go for the mean. So, but I might go for the natural log. Thoughts? You guys are like, Michael, we need to go to lunch. Yeah, okay. Just kind of curious. Like if the outlier was caused by artificial, then I kind of look at mean imputation. But if it's a natural outlier, I know it sounds weird. I might actually delete it just to see how the data performs. And you would delete the whole row to answer that question, right? But I probably would just take the log value, or yeah, that's hard, especially with income, because it's such a huge outlier. Like I'd have to look at the rest of the data set and see if there's any values between 100, 200, 300, 400, a million, all the way going up to 3 million. But man, if it is just out there all by itself, it's really going to skew the data. But in general, like, I would again probably take the log. Deletion would probably be a last resort. It also, by the way, depends on the business problem. If it's not going to really skew things for the business problem, move on. In other words, here's what you should take away from that. Here are some options, but you need to think contextually and holistically about what you're trying to accomplish, right? And you need to look at the rest of the data set to see if there's other close data points, or is that just such a huge outlier? And how much data do you have? Do you have 20 records, 100 records? That might be a huge skew. Now, I think from what we saw, we have at least 4,000 records based on what we saw from the shape of the data. But like, if we got, a 10,000, 20,000, 30,000 records, then that outlier might not have as much impact. But just throwing that out there. Think contextually before this. Missing data. All right, so we're moving away from outliers. So from extreme outliers, we're talking about missing data. This, by the way, could be a data collection error. You might be able to derive, for example, the age from a dimension that you didn't include in the data set. By the way, what would be like a relevant other like data feature, data dimension in your data set that might help you derive age? Sure, education could. Birth date. Yeah, date of birth. But people frequently drop that, right? Because if I got age, what do I need date of birth, right? And you might have correlated that, which hopefully did probably make sense. Maybe not, because it depends on the formatting of the date, right? Wait, participants for Florida. Anyway, so you might go and like impute the data just by doing a correct derivation of like, oh, well, they were born, 1965, whatever. It's like, let's go derive let's go derive the age, right? By the way, most ML algorithms are not going to deal with missing values automatically, right? So you really have to replace them. You can't leave them gapped, right? So if it's data collection error, fix the data collection. If it's data that you can impute or derive from another source, do that. Missing data can really make it hard to interpret the relationship between the related feature and the targeted outcome. So you just kind of have to deal with the issue. Mean imputation can do that. There's a couple of different methods. Obviously, a few like I said, a few missing values might not be an issue, but if you're missing from quite a few values, you got to figure out how to fill that in. So with Panda, by the way, if you're like examining the data, you can just check and say, look, how many nulls do I have, right? And you can say, how many missing nulls do I have for each row? So Panda, by the way, can help kind of like fill that information in and say, hey, how many of those are empty? And then which particular rows are we having problems with? Notice that the difference between the is null sum and the is null sum is just the inclusion of a parameter that switches the axis, right? From 0 to 1. 0 is the default. So you got to dig a little deeper, like, is it just an accident? Did someone fat finger, like, what are the mechanisms that cause the missing value? Is it that it was a set of 10 questions and questions 8, 9, and 10 are consistently missing values because people were exhausted? 10 questions probably wouldn't be enough. Let's say 30 questions, right? And so you really need to like check out your data to see like where the gaps are, where the outliers are, right? And any other kind of like deviations as far as standardization and formatting, right? Now, if you want to drop values, which again, be very careful with this. Data is the new oil, right? Isn't that the phrase everyone throws around since like 2019 or something? Be careful when you drop data, right? So make sure that you're doing it and it in a very intentional way and test it, like test your theory around dropping data. That might be one of the last things that I would consider doing, right? Is dropping data. I'm just looking at the rules down there. How equals all, thresh equals 4, threshold is 4. Huh. Anyway, it just shows the same thing that you saw with the previous one, where it's basically dropping null values and then, right, doing it along the column axis as well. Okay. The risk of dropping rows is significant. So if you lose a lot of rows, you may not have enough data, and then that's really going to bias the sample because you're not going to have enough, right? Dropping columns has a simple effect. Wait, did I say that right? I might have got my wires crossed. If you drop rows, if you don't have enough training samples, then it's not actually going to be able to do true analytics, right? It's not actually going to really be able to derive accurate predictions. It's just going to memorize the training data, right? If you drop a column, so not a row, but a column, you're going to lose information in the features, right? So you're not going to have enough features to feed the model, and so the model's not actually going to learn how to do its job, right? In one, it's learned the training data too well, which is overfitting, and so therefore it doesn't really do well in a production setting. And the other one, underfitting, doesn't do well in a production setting because it's actually slow. It didn't actually learn how to do the task. It's underfit. It's not fitting with our target, right? In other words, if you really want it to learn and analyze, you've got to give it a large variety of data in order for it to be able to derive the rules it needs to get to the outcomes you want. But if you train it too much, then it kind of like, it's almost like it's prejudgmental. It's like it just memorized the data that you gave it. It actually doesn't really understand the nature of the problem you're trying to solve. Make it sound like it's a human being, but I think the sentiment expresses the intention. Now, imputation. Right, we just talked about we're going to do imputation. So for example, here's a scikit-learn where instead of dropping those values, you can impute the mean. Now let's take a look at what happened here, like in a little bit of detail, and then we'll stop shortly just to make sure we're on our lunch. So 5, 3, 2, 2, right? So right, nothing really here. But then we have 3, 1, and 9, and instead what it did is it put 3, 2.5, 1, and 9. And then we've got 5, 2, 7, and none. And what it did is it imputed the mean of 5, 2, and 7, which would be 5.5 in this case. So this is an alternate way is by imputing basically the mean. You could also, by the way, here they imputed the median, right? So by the way, they can convert the income data into its natural log. This again reduces the numerical variance, making it the highest value so we can skew the data. So we can also use the median for that value, right? Some of the empty values were left empty since they were categorical and could not be replaced with numerical values. And those rows might still be useful to keep even though they have gap data, right? So okay, let's stop here before we go into data visualization for categorical and numerical data. Don't have any questions before we break for lunch?
I have a question surrounding normalization standardization. Were we planning on talking about that at all, or is that not as necessary for machine learning applications as it is for statistics?
I don't know that I wouldn't say it is as relevant. In my opinion, it is relevant. I will tell you that by the time I usually see the data, because of the data stores and other sources that it's pulled from, it's usually already standardized and normalized in some form or fashion. Sometimes I get access to raw data like clickstream data or IoT data right? But just by the nature of how that data is reported, it's usually already been standardized and normalized. I would love to hear other opinions around that, about the importance of standardization and normalization to data reception. I think it's actually still important, but I'm not typically involved in that. I don't usually have to do that because I usually receive data that has that done already. Any other thoughts?
I would say it's very important, especially when you're dealing with neural networks, because I've found that a lot of times you have to make sure you have strong normalization as well as scaling, because scaling can make a tremendous difference in terms of accuracy of models with the different flavors of artificial neural networks. At least that's been in my experience. I've had like models that seem to have fairly tight distribution of the numeric values, but then the model won't converge. It just kind of keeps spooling and spooling, and then you'll scale it, and then all of a sudden it starts starts to do what you need to do. So that's definitely something to keep an eye out for.
Okay, yeah, good. Okay, other thoughts? Does that answer the question, by the way?
Yeah, I guess it just takes practice on, like, being able to eye when you should do it, how you should do it. Because I think that's where I struggle. Is making that judgment call.
Yeah, I would say, what is that phrase? Premature optimization is typically a negative, right? So I wouldn't necessarily lead with that unless you see like a strong need for it right out of the bat, or historically, that you need to normalize and standardize just because you're either not seeing the performance or the data just in and of itself is too deviant, right? Yeah. So in general, I would like say start with the data that you get. But again, it also depends on your data source. Like I said, most of the sources I get, they've already been, optimized for whatever role they're about to play, not necessarily for my training model. So there might be further kind of like normalizations that I might do for that. So it's kind of a little bit of it depends, but I would start with the data you have, see how the model performs, and then just iterate and experiment, right?
I guess the other comment I would have is just that that's part of what anytime I'm performing exploratory data analysis, that's a big part of what I'm looking for. Particularly where you're looking at seeing how many levels that you have in the different columns, looking for variations like that. That was, I thought, a really good example with like how the income, sometimes it was per year, sometimes it was per month. But I think that, taking a good hard look at what you have when it comes in, a lot of times will, particularly just through experience and just understanding, if you have a situation where you need to try to make sure that you're describing the same thing in the same column, because it does come up pretty frequently, and sometimes it's a little bit harder to spot. But I think that's why it's always important to spend that a little bit of extra time on exploratory data analysis at the front end. It saves you a lot of heartache at the back end sometimes.
I definitely agreed. It's a little bit like next to the problem formulation, data pre-processing, exploratory analysis, visualization, examining the data from all angles, looking at the nooks and crannies. I mean, you don't want to overanalyze, obviously, but like having a standard set of exploratory functions that you execute against your data, especially as you like historically run into known problems, you can then just check for those problems. And since they're mostly executed as code, you can actually see those visualizations really quickly.
Another kind of tip that I would put out there too is what I have actually like a handful of notebooks that I keep, where I have sort of like a system that I go through, and I have some of the functions that I've found that work well for different things already plugged in there, and then I can just kind of pop that notebook in, bring in my new file, and start kind of going through those things. And that's a good way to make sure you're not missing steps, and it also keeps you from having to roll, bring up all these functions from rote memorization. So
right. Yeah.
It's actually a really good idea.
Yeah, and I gotta tell you, I do have a library of things myself that I have for a variety of different topics. Because I mean, if there's one thing that's true about our industry, the knowledge base isn't getting smaller; it just continues to grow. But what we have to do tends to continue to be narrow and deep as far as like how we manage these things. So creating your own library of useful, for example, data processing functions that you would normally do, totally valid, right? And notebooks make that so easy to do and share. So I don't know if you guys have an internal data scientist, data engineering channel at Booz that just like for general, but I've worked in a lot of places like ThoughtWorks and Red Hat and whatnot. where a lot of those things were widely available, and people would say, hey, what do you normally do for this? And you can instantly get a bunch of tools in your hands that would make that happen. Dakota, to answer your question, outliers should be handled before imputing values, right? Depends on how you're imputing the value. Like you're talking about like in that mean situation. Yeah, I mean, yeah, God, that's tricky. Yeah, I mean, I might exclude the 3 million if like has an outlier in terms of my mean computation, but you got to be careful with that, because if you're going to include the 3 million in the data set to begin with, and then you're going to kind of compute a mean that doesn't include that, again, I'd be inclined to either take the log of that and then compute the mean after I did the log, or like drop it all together. But I'd probably take the log of it and then compute the mean from there, right? So the answer to that is yes. The outlier needs to be handled in some form or fashion before you're going to do like mean imputation. Okay, so we're going to stop at data visualization, and we're going to pick this up. We're about halfway through this section. It's 12:06 right now. So why don't you come back at 1:09? That is 63 minutes from now. We're going to finish this section on data preprocessing. We're going to do a lab. You're going to get hours to do the lab, and then we'll go from there. Okay. So I'll see you in 63 minutes. I'll put up a timer. Okay. All right. So visualizations for categorical data, right? So in this case, it's, do we have high school diploma? Do we have a 4-year degree? Is it a master's, PhD, right? So you can go back to like a descriptive table and kind of like visualize the education data and data set it and compare it, with kind of like the general population. So we can tell, by the way, that by looking at it, what stands out here, by the way, what is being underrepresented in our data set population versus general population analysis? Like think of the right as demographic data. What's wrong with our data set? Yeah. So, and you can look, it's underrepresenting high school diplomas, and it might be overrepresenting, maybe except for the 4-year degree, the no high school diplomas, the 2 years degrees, and the masters and PhDs, right? So you want to keep this in mind as you evaluate a model, because you might want to ask your data scientist or engineer or whatnot to perform some transformations to help compensate for the problems. But this kind of visualization can kind of give you a feel for like the data. Now, does the data set population have to be representative of the general population? Not necessarily, but it might be something to be aware of. Like these kinds of comparisons, you might compare your data set against like publicly available data just to get a feel for how it compares. Sorry. I just want to say that, Chris, I like your statement around pipe and tab delimited have fewer issues. Yeah, and it all depends on what the client's willing to do. The formats they're willing to send it to. But typically, it's all going to come out of a spreadsheet, or I rarely get like, even the database administrators are like, here you go. Like, can you give that to me in Parquet? And they're like, what? So no, I'm just kidding. Most of them know what Parquet is, but they won't do that. Here you go. Or like the screenshot thing that was it Dwayne was mentioning earlier. So this is a great way. So visualizing data can give you an idea to spot deviations, underrepresented outliers in some cases, right? Not single outliers, but just general skews. Maybe outliers not a better word. General skews in your data. So nix that I said outliers. And then numerical data, right? You can see these huge gaps here. So if we were to, for example, to bend this and put it into a histogram, right? It's like, is this a normal distribution of features, right? So values, by the way, when they're bend, are kind of like stuck into a range, right? We're going to talk about this more when we talk about feature engineering and model tuning, right? So, it's like how many peaks are there? Is there any skew in the data? Is the data like normally distributed? Is it supposed to be? The answer to these questions, the data may be fine, but these are just questions to ask when you're exploring it. Now, you're gonna use Panda, for example. Here you can create a histogram by using the Panda hist function. So you just set up your data frame, including length and width. Index, pig, rabbit, duck, chicken, horse. That's funny. And then just do it histogram with your bin size set to 3. Other common things other than a histogram would be like, for example, a density plot, right? So like particularly for numerical features, in addition to a histogram, density plots and box plots, which is what the right-hand side is, to get an idea of what's like inside a particular feature. So these visualizations are going to help you answer questions like, what's the range of the data, the peak of the data? Are there any outliers? Are there any special features? It's going to help you understand the data, but decide if you want to like do something more specialized, like in terms of pre-processing. So density plot, by the way, is going to plot the distribution of a single feature. So the density plot is similar to a histogram, but plots a smooth version of the histogram density, and it uses a kernel density function. Another way, by the way, is a box plot, and the box plot uses like basic quartile ranges or interquartile ranges to plot the distribution of the features. Now, when you're looking at for relationships between more than one variable, you can look at what's called multivariate stats, right, or statistics. This only has to do with correlations when you want to see if something increases in relationship to each other or inversely increases and decreases, or if it's like zero, neutral, there's no relationship between the attributes. So when you have multiple variables that you're looking for, right, you might want to look at correlations between them, because high correlation can sometimes lead to a very like not awesome model performance. So and also you might remove the correlated feature if one of the variables in the correlation, if it's unnecessary. So the problem here is that when features rise at the same time in value and they stay in lockstep and they're using the same model to predict the response, right? There could be problems because the model loss may not like converge to the minima state as far as errors that you're looking for. So you want to be aware of highly correlated features in your data set. Now, when you have two numerical variables in a feature data set, sometimes you want to look at their relationship, right? And a scatter plot, right, is a really good way to spot any spatial relationships between variables. So in this case, on the left, the y-axis, you have version 12. On the bottom, you have version 11. Now, this is from the breast cancer Wisconsin data set, and that's the source data set. And as you can see, there are plots that are scattered all around. And so even though the correlation among them may not be high because the data is scattered around quite a lot, there's typically some positive relationship between the variables. But there are clusters there. So, although it's a pretty interesting spread there. Maybe use that for an example. Here's another scatter plot. This is a scatter plot and then a scatter plot matrices, right? So scatter plot matrices is going to let you look at multiple features, so multiple variables, if you will, at the same time, right? So it's going to show you like version 11 of feature version 31. It's going to give you a plot for that. And notice that these scatter plot matrices, where they intersect is the two versions that we're looking at. (15 by 15) figure size. That's funny. Here's a scatter plot with identification. So you might want to identify special regions that fit a particular subset of data. So here, by the way, they've basically created a chart that shows malignant and benign patients. You can see that there's a clear, kind of line there where the two start to overlap, but there are obviously some over the line, some under the line on both sides of the equation. So even though they can't be separated perfectly, there's indeed some power that can be used to distinguish between malign or benign patients at a certain value or threshold of probability. So this can be useful to see how particular variables, by the way, could actually be helpful to say, do you have cancer or do you not have cancer? So a classification problem, right? Because notice that it's not like there's a bunch of far-reaching reds all over. There is actually a point in time where it's just blues, and there's a point in time where it's just reds. Where that line lives, right, probably depends on how many false negatives and false positives you're okay with, right? People don't want to miss cancer typically, so you might want to keep your false negatives down. So you might want to be a little bit more aggressive around that. We'll talk about stats, by the way, that favor false negatives over false positives and pieces like that later when we do model evaluation. Oh yeah, so correlation matrix. So this is where, remember, correlation is when a variable, like there's a relationship between the two variable numbers and they rise at the same time, or there's a negative relationship and they're inverse, right? So one goes up, the other goes down. Like revenue and sales, right? Income, like those typically have some kind of ratio of correlation. So if it's 1, if the correlation is the value of 1, it means that it's a 1-to-1 lockstep ratio. If the value is -1, it's a 1-to-1 inverse relationship. If it's 0, then there's just neutral, right? So here with the correlation matrices, obviously the relationship of F0 to F0 better be 1, or fundamental mathematical equations are probably broken in the universe, right? So I will tell you that sometimes with a lot of companies, you might use something like PCA to kind of remove highly correlated values by, aggregating them if there's a high correlation between them. Most companies that I've dealt with, if it's 0.8, 0.9, they don't, you might remove those values because there's too much correlation between them. And again, it just depends on what you're trying to achieve with your model. By the way, for example, if correlation is 0, it means there's no linear relationship. Just to be upfront about that. Doesn't mean there isn't a relationship. There's just no linear relationship between those two variables. This is useful, but like heat maps like this even make it even more useful. Sometimes it's view the numbers themselves and to see them kind of represented by color. So this is a heat map, right? So the highest number 1 is in green, and I don't think there's any -1s, although those -9s, 0.9s are pretty close, right? The color gives you the positive, negative directions. It really says how strong the correlations are. So you can see that, F4's correlation, at least with the first 4 variables, 0 through 3, fairly low, right? So, and you can see that the first 4 also have a low correlation with F8 as well. These kind of colorful ones, by the way, are mainly done by Seaborn. So remember, it works on top of Matplotlib to kind of provide more enhanced, more colorful, variegated visualizations. Obviously there's a bunch of like math around this, like, like for correlations. By the way, well, 1, this class is not going to dive into this, but 2, just know that there's nothing on this on the exam, and there's barely any of this in the AWS documentation, right? And so just know that AWS's job is to try and abstract away some of the more complex and deeper level mathematics. So you're not going to see any of this. This is just here for reference. It's here for funsies. Standard deviation. Okay, yeah, anyway, moving on. Not going to get into that. It's a rabbit hole. Way too much fun. Okay, so this is what we did basically when pre-processing the data. But before I do this, does anyone have questions about any of these visualizations? Heat maps, scatter plots, scatter plot matrices, density plots, block plots, histograms. Any questions about any of that?
Can you go back 1 or 2? Keep on going. Keep going, please. I think it had 2 charts on it.
Say again?
The one with the V1s to the V3s.
This one?
Yes, the one on the right side. Can you remind me what this means?
The scatter matrix, it's
Yes.
it's basically just a matrix of scatter plots. That's what it is.
And what about those histograms on the along the diagonal? I assume that would be V11 and then V22 and then
Mhm.
V33.
Exactly.
So is that just oh, it's just a histogram of that particular feature?
Yeah, exactly.
Okay.
Right, because it's the feature comparing to itself, so it's just right. Scatter plots aren't gonna really make any sense because the values it's correlating against itself, right?
Yeah, it would just be a line.
Right, exactly. So good. Other questions, Chris?
Okay.
Or anyone? Okay. Okay, so here's a quick reminder. One, we talked about S3 because that's object storage, doesn't mount inside of an operating system. We talked about it has multiple layers, like it has infrequent access, it has hot storage, which is just standard, and it has Glacier. So just a reminder, cheapest is Glacier, but it's not directly accessed. Next cheapest is infrequent access. And then of course, the hottest and most like consumable storage is S3 standard, which is probably where most of our jobs are going to run from. You're not going to run from an infrequent access or Glacier. But if things need to be cheaper archived, then basically you can use, right, the you can use the Glacier to archive it out. Infrequent access to still host it even though it's cold. But if you want to run it, you want to have S3 standard.
I got a quick question about that. So, okay, so for the Glacier, obviously you don't have direct access to it. So that's kind of the drawback to it in terms of it's cheapest, but you don't have the direct access. So that's sort of the penalty that you pay on it. So what about the one between like the hot storage, like whatever that kind of middle one is? Is there like more latency when accessing that versus the regular hot storage, or what happens? Like,
No, it's not slower, but infrequent access will charge you if you make a bunch of API calls to objects at the same level that you make them to standard. So
okay. So
yeah,
there's like it's like is there like some sort of like a limit on it on how much you can access it or whatever before they start kind of penalizing you?
yeah, so there's you know, I can't remember the number off the top of my head, but I want to say it's like you get like 1,000 API calls, like read calls a month against every object.
Okay.
And when you go above that, it starts charging you. But I don't remember the numbers for pricing off the top of my head. But when you cross a certain threshold, it starts charging you like for more frequent access. Whereas if you're frequently pulling files down and accessing them, pulling them, read them, manipulating them, then they want you to use standard and not use infrequent access. So infrequent access is when the file is very infrequently touched. So maybe like 5 to 10 times a day or something along those lines. And just to say this, Glacier tends to be Glacier Deep Archive is 1/24th of the cost of standard. So as you go down the tiers, they usually drop from like 100% to like 80% and then 60, and then you're down to 50, 40, and then all of a sudden you're down to 5. It's really, really weird how far down it goes and how quickly, especially when you get into Glacier and Glacier Deep Archive. Now, just to be clear, intelligent tiering will automatically put your files at whatever level of access that you're doing. And if you're not accessing it, it's going to put it in colder storage. Now, if all of a sudden you start accessing Glacier, it will instantly expedite and restore the file back to whatever tier of storage it needs to, and you won't pay any money. But just so you know, you only use that for data where the access pattern is unknown, because they're going to charge you per month. Sorry, per object. They're going to charge you a monitoring fee. So over and above the hosting storage costs, they're going to charge you a really, really tiny monitoring fee for the object. So just know that intelligent tiering will move your data up and down to the right tier depending on how you're accessing it. And then you don't have to do any lifecycle management rules for the data, right? Intelligent tiering will automatically move you to colder storage. If you don't touch it, it'll move you to hotter storage, but there's a slight surcharge. Is that more expensive than you doing it manually? Yeah, if you're not going to manage it, yeah, it's not more expensive. If you're not going to manage it, then you should probably stick it in intelligent tiering and just let intelligent tiering handle it. If you've got really clean access policies and you know after 60 days, this data needs to go in the Glacier, and after 30 days, this needs to go into infrequent access, then if you've got really clean policies like that, then it's easy to do. If you don't have clean policies and you don't know your access patterns, intelligent tiering in S3 is going to be your friend. Okay. Let's see. So, that was a correlation matrix, not a confusion matrix. Make sure we're clear about that, right? Yeah, so let's see. Identify which features will incur collinearity issues because of correlation. Yeah. Yeah, in other words, if there's highly correlated values, right? Because you're visualizing, this is pre-processing, right? You might need to go look and say, do you need to keep both of those values? Right? Because, for example, just simplifying it away from the heat map, right? If, you know, it's in this situation, it's probably good to remove highly correlated values, because if you don't need both of them, this could cause trouble with your model training, right? So with this kind of matrix here, like the correlation matrix, it just allows you to quickly identify where the high correlations are, so that when you do your data exploration, you can find out, do you actually need those values? Maybe you don't, or maybe there needs to be some kind of transformation to happen that needs to happen to them. Does that make sense? Yeah. So this is just to aid the human eye in identifying where there might be a correlating pattern that you might want to reduce. Okay. We talked briefly about like Panda and Seaborn and Matplotlib and Scikit and NumPy. Basically has library modules that you can import into your code. You're going to see that actually in your lab today. We talked about using pandas to like do data reframes, like to put columns and change things. You can also use Panda obviously to drop and manipulate data as well if you want to drop null values. Talk about some of the challenges around like missing data, things in the wrong column, bad delimiters, extra delimiters, right? Delimiters included in values, which then become delimiters themselves. So that can be all confusing. Some visualization techniques, looking at scatter plot matrices, density and box plots. And then, what you might want to look at when looking at relationships between one or more variables, as far as like positive and negative correlation. So, good. Okay, so let's talk about this next lab, because it's going to frame us up for the next couple labs. So lab 2 is that we're now moving on to data pre-processing. So the next 3 labs are going to consist of a practice exercise, and then they're going to consist of a project application. So you're going to do an exercise where you're going to do data pre-processing, and you're going to like mess with these things. And then you're going to open up your project file, your notebook, and you're going to apply what you learned into your project file. You also have a solutions file that will also help you if you need to check and see, like, am I framing this up in the right way? So the first part of each of the lab is a practice exercise. Second part, work on your project. So, and I can remind you, it says this here, right? Make sure you download the notebook after you complete each lab. And what did I say that you are not to do once you're done with your lab? What did I say is the one thing you're not to do yesterday? What did I ask you not to do after you're done with your lab today? That's right. Anaya, that's good. Yeah, don't end your lab. Don't end the lab. Don't end it. Just trust me. If you forget or mess up or whatever, that lab's going to run for another 8 hours or 7 hours or 6 hours after we're done. So that way you can just go back and grab it. It's still in there in Quick Labs. You just need to go switch to the view, open the lab, and you can go grab your files, right? So remember, they're not going to shut down the AWS account until the timer expires. So if you don't hit end, it's just going to sit there and run. And I know you're like, but Mike, I don't want to waste. No, it's okay. We're not wasting resources. AWS is still getting paid. They're fine. So, okay. So I'm going to talk about it, and then I'm going to just show you really quick what this is going to look like. Okay. So you're going to log into SageMaker. Well, first of all, you're going to log into your account, and then you're going to click on SageMaker. And then you're going to open the PE data processing basically notebook file. Now, I'm going to tell you this is not going to happen. We're not doing that because we're also not doing the presentations and the share outs, right? Don't get me wrong. You can ask questions at any time. You can ask questions of your peers at any time. But you're going to apply basically what you learned here over here to your particular project, whichever one you decided to do. When you're done, you're going to save and download your work. Now, notice I said download, which means you're going to go file, download the actual notebook. So the, the IPYNB, right? Okay. So let's dig into this a little bit more. For those of you who are comfortable, obviously, you can just go ahead. I think I logged in already. Either that or I am suffering under illusions. Oh, no, I did. Hold on. Let's see. All right, so this is the machine learning pipeline. So for me, I'm going to go over here and open the lab. Let's say I open the console. Now, notice that, my password manager is filling stuff in. So I need to make sure that one, the account number is right, which it looks like it is 644. I'm going to go ahead and copy my password. Need to change this to AWS student. If you're logged into another site, another AWS account, by the way, please log out. It'll make things easier. I'm not going to save this because it's just going to change every time. Notice I'm checking my console. Am I in the Oregon region? Yes, I am. Good. Let's move on. All right. And then I'm going to go into SageMaker. And then notice there's all this stuff on the left-hand side. I'm going to click on Notebook instances. Now, your instance should be up and it should say in service. And then I'm going to click on Open Jupyter. And by the way, this is all in your instructions. So I'm not doing anything, right, that is not in the instructions. Now, this is a little bit of an eye chart. So you're going to work in this data processing file. I think I have another instance of it open, so I'm going to close that down really quick. So this file is just like the one that we first worked in, right? It's got code in it. You're going to run it. You can do Shift Enter if you want to run, right? But you're gonna run this. Now notice this has an asterisk, so it's just sitting there running right now. You're gonna run through this data pre-processing setup, right? This is gonna show you things that you could do to pre-process your data. When you're done with that, you're gonna come into your project and you're gonna open up whichever one you're doing. So let's say you're doing credit fraud detection. You're gonna open up the one that doesn't have a language code after it. You're gonna open that up. But I do want to point out one little thing. Down here in the pre-processing lab, you're gonna see things that say every once in a while you'll see something that says enter your code here, and the code's already going to be there. Just ignore that, right? So it says enter your code here. What was happening is that people were getting really hung up on figuring out how to do the data processing that they were never getting to their project. So we're literally think of this as you just walking through and kind of looking at the concepts around how data processing can be called, how to describe your data, how to get density, shape, dimensions, and all those other pieces. And then what's going to happen is that you're then going to apply those concepts to your project. Now, I chose credit card fraud. So not only am I going to open the credit card fraud notebook, which this is the one that you're going to download. This is the project file that you're going to go to File and Download when you're ready to do it. You're going to download it as a notebook. But you're also going to come back here and you're going to click on these double dots one time, by the way. Click on the double dots one time. If it doesn't respond, just give it a second. It's thinking, right? And then you're going to come into Solutions. And since I'm doing credit card fraud detection, I'm probably going to go ahead and open up the credit card fraud detection solutions as well. Now, this is where it's going to actually have a recommended way to approach, notice it's not going to have problem formulation and all that stuff, right? But ways to do setup, and I'm not going to scroll too down on that, okay? If you're new to data science, you're probably going to spend most of your time in the solution porting that over. If you're not new, if you're an actual data scientist, and by the way, if this just bores you because you're I've solved this problem a million times, you don't have to. But just know that you're going to spend most of your time in the student project file. Okay. Now, when you save this to your local system, not the system out in the cloud, but your laptop or desktop, I would recommend that you might just want to go ahead and make a backup copy somewhere else on a USB drive, email it to yourself. That sounds silly, but in the history of this class, people have actually lost their files because their laptops went belly up and they lost 2 labs worth of work. We got the solutions. Labs are independent from each other, by the way. So it's not like you have to complete lab 2 in order to lab 3. The other thing I want to point out is that in your student project file, not the solutions file, not the data preprocessing, which is the lab, if you scroll down far enough, it'll say end lab 2. You are going to stop here. You're not going to go on to model training and evaluation. That will probably be tomorrow. Okay. This is it. We got 2 hours. So what you're going to do is you're going to roll right into doing the pre-processing. You're going to run through that one. When you're done, you're going to open up whatever your project you're doing, either credit card fraud or recommender for videos or the travel weather one for the plane flights. And you're going to open up the student one and you're going to open up the solution. Any questions? Okay, let's get to it. Any questions, please post them publicly because you're probably going to help out 5 other people. I'm going to apologize profusely. I need like 5 minutes to take care of something. I promise you it's urgent. So, yeah. And when I come back, I'm going to answer questions if they're available. I am going to work on posting the videos because I know more than one person just asked me about them. So, yeah. Okay. All right. I'll be right back. I apologize. I'll be right back.